Okay, last class. We left off talking about strong bases in determining concentrations of hydroxide in solution. There are two types of bases. What's one of our types of bases? Strong bases and weak bases. How can we identify in this class a strong base? There's two things that we'd be looking for. The hydroxide is one of them. So we see the OH and we think, oh, that's a strong base. The other thing that we're looking for is it paired with a cation? Is it paired with a metal? So it's ionic and has hydroxide. For us, that means that it's a strong base. The other circumstance that we can have, the weak base. Weak bases tend to be amines, at least in this class. So that means that it has nitrogen in it, essentially. So when we're calculating hydroxide concentration, strong bases are going to produce full equivalents of hydroxide. So if there's one hydroxide in our compound, each of our strong bases is going to go to make one hydroxide in solution because it completely separates out into its ions in solution. If it's a weak base, it's not going to go all the way to one equivalent, and so it's going to be less than. We're not learning the tools to cover the gaps in between, which is great because that means less math for us. So we're looking at a couple of solutions here. We want to determine first if they're a strong base or a weak base. So looking at CaOH2, is this a strong or weak base? It's a strong base. We know that it's a strong base because it's got hydroxide. We say, oh, that's a strong base. So we know it's a strong base. And how many hydroxides are there? 2 hydroxides for each CaOH2. So if we want to know how many or what concentration of hydroxide we have in solution, because that's what we're looking for, hydroxide concentration. There's 2 hydroxides for each calcium hydroxide. We're going to multiply this 0.135 molar by 2. So 0.135 molar CaOH2, calcium hydroxide. There's 2 hydroxides that will be produced for every 1 calcium hydroxide. So we're multiplying by 2. Our concentration of hydroxide is 0.270 molar. Not too crazy as long as we remember that this subscript of 2 means that we have 2 hydroxides for every 1 calcium hydroxide. So it's going to double the concentration of hydroxide compared to the calcium hydroxide. For NH3, we're looking for a hydroxide concentration. What kind of base is NH3? Strong or weak? Weak. Why is it weak? It has a nitrogen in it. And that's kind of all that we talk about weak bases. That's good enough for us. So ammonia is one of the ones that we'll see. There's also pyridine, C5H5N. Those are 2 that you could see on an exam. So that's going to be a weak base. So it's going to produce less than 1 OH minus for each NH3. We're going to have some NH3s in solution. We'll also have some NH4 pluses and hydroxides because it's accepting a proton from the water. So for this one, it's just concentration of hydroxide is less than 0.95 molar. We don't know what the actual concentration is because, again, we are not learning those tools, which means a lot less math for us, which is huge. We love that. All right, last one, KOH. What kind of base? Strong. Why is it strong? It's got a metal and hydroxide, OH. So we see, oh, that's a strong base. The more I say it, the more it'll get stuck in your head. That's why I'm doing it. How many hydroxides do we have here? One hydroxide in each KOH, 1-to-1 ratio. We love multiplying by 1. At least I love multiplying by 1. 0.50 molar is our concentration of hydroxide. Questions about any of those? Okay, recall. Water is amphoteric. Amphoteric means it can act as either an acid or a base. If you get pure water, which you'll never do, you can get pretty close. You're never going to touch pure water. You're never going to see it. You're never going to smell it because it's scentless. But also you'll never be close enough that you could smell it. But you could get pretty close. Impure water, water will act as an acid and a base, just with itself. It's bored. I don't know. So water, one of them acts as an acid, the other one acts as a base. What does the one that's an acid do? Yeah, it's giving proton, giving H+, hydronium. And the base is accepting or receiving the H+ to form our conjugate acid, that's the one that can act like an acid, and our conjugate base, that's the one that can act like a base. We call them the conjugates because they're on the right side of the equation. So water will do this, and when it's just by itself, it does it. So there will be a small amount of H3O+ and a small amount of OH-, equal amounts, just with water. That self-ionization occurs to a very small extent, and it gives us equal concentrations H3O+ and OH-, because they're both coming from water. For one to form, the other also has to form. If we have pure water at 25 degrees Celsius, those concentrations are equal, and the concentration is 1 times 10 to the minus 7 molar, or 0.000001 molar. So small you can hardly tell that it's there. We've got a term, the ion product constant for water, K for constant, little w for water. That's what happens if we multiply the hydronium concentration by the hydroxide concentration. That value, because they're each 1 times 10 to the minus 7, when you multiply things, the exponents add together. So we get 10 to the minus 14. 1 times 1 is 1, 10 to the minus 7 plus 10 to the minus 7, or adding the 7s, we get 10 to the minus 14. And this is usually expressed without units, because we know what the units are. Or we could figure them out if we're an experienced chemist. In a neutral solution, not acidic, not basic, but somewhere perfectly in the middle, our concentration of hydronium, our H+, is the same as the concentration of our hydroxides, our OH-, is the base part. We're going to be using these a little bit. You may remember that last class I said we're going to do the math stuff today. We're doing the math stuff today. So this is where we're getting some of that math stuff. I usually give you a lot of the things that we're covering today. I usually give you the equations, so you don't have to sweat about those. It's also a little too cold outside to be sweating. So, in a neutral solution, we saw this on the previous slide. The concentration of the H3O+ is the same as the concentration of the hydroxide, which is 1 times 10 to the minus 7 molar. That's our neutral ground. In an acidic solution, our concentration of the acid part is greater than 1 times 10 to the minus 7. And the concentration of our hydroxide is less than 1 times 10 to the minus 7. So in an acidic solution, more acid than base. These can get a little confusing because we're in the realm of negative exponents. So a smaller number, like -5, would be a bigger value than, say, -7 or -12. In a basic solution, it's the opposite. We've got more base than acid, more hydroxide than hydronium. So our hydroxide concentration is greater than this neutral amount, any number greater than that neutral amount, and our hydronium, our H+, our protons, is less than that neutral amount. In all of our aqueous solutions, at 25 degrees Celsius, our concentration of H3O+ times our concentration of OH- equals 1 times 10 to the minus 14. This means if we know our hydronium concentration, we can figure out our hydroxide concentration. If we know our hydroxide concentration, we can figure out our hydronium concentration, our H3O+ concentration. The two things are related. When one goes up, the other goes down. When one goes down, the other goes up. We tracking? Hopefully. I'm seeing some nodders in the chat. Okay, some examples with numbers, both as long form and short form, shorts and full videos. In an acidic solution, if our H3O+ concentration is 1 times 10 to the minus 4, in decimal form that looks like this. It's going to have a hydroxide concentration of 1 times 10 to the minus 10, which is going to look like this. So 10 to the minus 4 is bigger than 10 to the minus 10. That's what I was talking about earlier. So it might be helpful if you come to a problem with negative exponents. You might want to think about writing them out in the long form. We can see this 0.0001 is much greater than this other number, right? Because the 1 comes way earlier. A basic solution with H3O+ concentration of 1 times 10 to the minus 9, it's going to look like this. The hydroxide then is going to be 1 times 10 to the minus 5, which looks like this. This is the bigger one. So it's basic. It's got more base than acid, so it's basic. Any questions or confusions so far? Cool. We can do stuff with that. We can use kW. So let's look at some examples. We want to calculate H3O+ concentration in each of these solutions. We want to figure out, is the solution acidic? Is there an excess of acid, H3O+? Is it basic? Is there an excess of base, OH-? Or is it neutral, perfectly balanced? To do these, we need our equation for H3O+ times OH- equals Kw, and Kw is 1 times 10 to the minus 14. This is only true at 25 degrees Celsius. We're just going to always assume that we're at 25 degrees Celsius because it's a nice little room temperature number. So if we are going from hydroxide, that's here, to H3O+, right? We're starting with hydroxide. We're going to H3O+. We need to rearrange this equation. So our concentration of hydronium is equal to 1 times 10 to the minus 14 over our hydroxide concentration, and that's going to give us some number molar. This looks sort of like one of the problems, some of the problems that we saw on the quiz, because you need to be able to put these into your calculator. You don't necessarily need to know how all the details work. You don't need to know how to do all the math by hand, but you should be able to put in the numbers. Something fell somewhere. Was not a tree in the woods? Okay, so we're taking this 1 times 10 to the minus 14 underneath it, we're putting 1.5 times 10 to the minus 2. Calculator says 6.7 times 10 to the minus 13. Divided? We divided? Great question. How do we put this in our calculator? The way that you put this into your calculator, one of the ways you can put it in your calculator is 1 times 10 to the minus 14. Depending on your calculator, you might have a little button that's 10 to the, with a little square in the corner. You can use that. You might be able to just like, there's a little X with a square in the corner, so you can write the 10, press the little X with the square in the corner. That'll be the place where you can put in the minus 14. You put in the minus 14, you press right arrow. That's our number that goes on top. We're going to divide, and we need parentheses for the stuff that's on the bottom, if you're writing it out. So then we put in our 1.5 times 10, hit the thing with the square button. Optionally, close your parentheses. If you do this in Excel, Excel will complain. You didn't close your parentheses. Would you like us to try to fix it for you? And then they'll just add in the, but on your calculator, it won't complain at you, so you can optionally leave it off. And then you press enter. And that should get you the correct answer. There's also another way, a faster way, that involves dolphins. It's the dolphin key. The dolphin noise key, the small capital E. Not the small lowercase e, the small capital E. You might have a button on your calculator that looks like this. You can press this double capital E key, and it'll put in one of these. And what this little e stands for, this small big E, small capital E, means times 10 to the, and then the number that follows it. So we would just write 1 small capital E negative 14 divided by 1.5 small capital E negative 2 equals. One of the advantages of using this little E key is that it connects these two numbers in your calculator. It says these two numbers are together, do not separate them. If you write it out this way, the previous way, the 1.5 times 10 to the minus 2, your calculator does not connect these two numbers. That's why we need the parentheses there. If you don't put the parentheses there, then you're doing 1 times 10 to the minus 14 divided by 1.5, and then you're multiplying by 10 to the minus 2, and you'll get the wrong answer. You'd get times 10 to the minus 15 or something. $16, maybe. Questions about that? Yes?
Where did we get the 1 to the 10 to the, yeah, that one.
The 1 times 10 to the minus 14 is our KW constant.
Okay. So it's always going to be like that.
It's always going to be like that in this class. In the real world, it will be different depending on the temperature that you're at.
Okay.
Or the temperature your water's at, rather. Other questions? Great. There is a way that we can check approximately that we got the correct answer that I'll show us at the end. All right. 6.7 times 10 to the minus 13. Is this a bigger number or a smaller number than 1.5 times 10 to the minus 2? Which one is bigger? Discuss with a neighbor. Okay, what if our discussions brought to light? Which, the one that's bigger is the one that has the smaller negative exponent. So 1.5 times 10 to the minus 2 is bigger than 6 and some change times 10 to the minus 13. That looks like B I guess that would also be, well, it depends what B is. Why is this important? We're supposed to determine if the solution is acidic, basic, or neutral. This 1.5 times 10 to the minus 2 is our amount of hydroxide. It's bigger than the amount of acid that we have, so we've got more base than acid. That makes our solution basic. So our first solution is basic. Our next solution, this one we actually don't have to do a calculation necessarily. So 1 times 10 to the minus 7. If we recall, in a neutral solution, H3O plus equals hydroxide, and 1 times 10 to the minus 7 is that magic number. That means this is neutral. H3O plus concentration is the same. Or you can also do the calculation. I'm going to not do it. You're welcome to try it. You'll get the same number. And then our last one it's the same formulae. So we're doing 1 times 10 to the minus, not 10, 1e negative 14 if you're doing the fast way, over our hydroxide concentration, 8.2 small capital E negative 10 equals, let's find out, calculator says 0.0000112 and some change molar, or 1.2 times 10 to the minus 5 molar. So that's our H3O plus concentration. What's bigger, 10 to the minus 5, 10 to the minus 10? 10 to the minus 5 or 10 to the minus 10? It's 10 to the minus 5, meaning that we've got more acid than base, so it's acidic. This is an acidic solution. The way that we can check with these, a rough check to see if things worked out, our H3O plus concentration times our OH minus concentration will equal 1 times 10 to the minus 14. So you could plug them in, multiply them together. You should get out something that's close to 1 times 10 to the minus 14. A faster way to check without plugging everything into your calculator, most of us, hopefully all of us, can add single and double digit numbers together. If you don't, you have a calculator, you can have your calculator do it. So what we're going to do is we're going to look at what's the exponent for our H3O plus, what's the exponent for our OH minus, does it equal around 14, negative 14? So for our first example, 10 to the minus 2, 10 to the minus 13. Add minus 2 and minus 13. Negative 15. That's in the, it's always going to be plus or minus 1 from our exponent here. So we got minus 15 for our exponents, adding those together. That's close to minus 14. That means we didn't screw something up horribly. If you get a number that's different by more than 1, something is wrong. Go back and check your calculations. So if you got like minus 16, minus 17, you did something wrong, go back and run the numbers again. Add more parentheses. 10 to the minus 7 plus 10 to the minus 7. Minus 14. Perfect. Our later example, 10 to the minus 10, 10 to the minus 5, minus 10 minus 5, minus 15. We're plus or minus 1 of our 10 to the minus 14. That means we probably didn't screw up, at least not too horribly. So that's a way that you can check it. As much as we all love scientific notation, there is a different way that we typically express our concentrations of acids and bases, and that's using pH and one you've probably not heard of, pOH. You've maybe heard of pH. So pH is much more common. We'll talk about what pH is. We're looking at some pH scale stuff here. If our pH is equal to 7, that's a neutral solution. If your pH is below 7, for example, 1, that's going to be acidic. A lower number is more acidic. If your pH is above 7, then it's basic. On a scale from 0 to 14, 0 is the most acidic. You can also have negative numbers, but that doesn't normally happen. Hydrochloric acid is in the ballpark of 1. If you just have hydrochloric acid, your pH is around 1, very acidic. Lemon juice is somewhere between 2 and 3. Pure water is 7. Our blood is slightly basic. It's a little bit above 7. And things like sodium hydroxide, bleach, Drano are in the like 13 to 14 range. You can also buy some fancy waters that are like, this is from a unique volcano in like the heart of Hawaii. I was going to say some crazy country. But Hawaii makes sense. And they'll be like, this is pH 8.88. Cool, I just want to drink water. But thank you for that. So you'll sometimes see it on fancy water. You'll sometimes see it on cleaning products. You'll sometimes see it on like products that are for your body. They'll often say stuff about whether they're slightly acidic, basic, or neutral. Questions about our pH scale. You should know this. Cool. So where do we get that from? pH is calculated from hydronium concentration. Here's our formula. This P, the little p, means negative log, just kind of generally. And the H here is standing for H+, which is the same as H3O plus hydronium. If you're interested in how logarithms work, here you go. There they are. I'm going to choose to not talk about it this semester because we're a little short on time. And it's cool, but it's not that interesting. If you have questions, I'd be happy to explain it. I love to yap. But generally, we're using this thing. Your calculator should automatically put in parentheses for you to put your number inside when you're doing log. Also make sure that you use the negative button. Instead of the minus button, because those are different. If you try to use the subtract, it'll probably just say, what do you mean, syntax error? That doesn't make sense. You should use the other one that's slightly shorter and usually has parentheses. So you absolutely need to know, by the way, how to put logarithms into your calculator. You do not need to know how they work. You don't need to know the nuts and bolts of how they work. You just need to be able to put them in your calculator and to be able to undo them as well, which we'll talk about. So as long as you can put them in your calculator, as long as you know when to do the calculation, you're set. All right, so pH equals negative log. Make sure it's the one that spells out log, L-O-G. It's different from ln. ln is the natural log. It's also a logarithm, but it's not the right logarithm. It's the wrong logarithm. So negative log concentration H3O+. So if we want to calculate the pH for this first solution, we say calculator. Calculator says yes. What is it? Please calculate negative log 5.8. You can also use the small capital E here, but let's write it out. Times 10 to the minus 4. I hate it. All right, restarting the 4. There we go, that's better. And then we press equals. You might have to press your log button twice to get the actual log instead of the ln. And you should get out 3.236 ... That's your pH value. The significant figures for logarithms are annoying. So the number of significant figures that we have for the number that we put in is the number of decimal places that we put for the number that we get out. It's not an issue that you should encounter, but just in case you were curious, I know that none of you were, but if you were, on the off chance that you were, I believe that is the correct way that they work. So 3.24 is the number that we would report for our pH. Do we have questions about that? Please put in, no, don't do the second one, because that's, never mind. We should have done the first one. It's fine. It's whatever. Make sure that you put that in your calculator and you get the correct answer out. Because if you don't know how to do it on the final exam, tough. Okay, for B, pH equals negative log 1.0 little capital E minus 7 equals 7. So the pH is 7. You put 0.00 if we want to. If you want to see, if you want to check with your brain, if you want a way of how we can identify if we did this incorrectly, your exponent for the number that you put in should be about the same, plus or minus 1, but not negative. Should be about the same number as you get out from your calculator. So we had an exponent of negative 4. So 4, we got 3.24. That's plus or minus 1. No issues detected. 10 to the minus 7, we put it into our logarithm function. We got out 7. Great, that's plus or minus 1 of 7. Perfect. We probably didn't screw up, at least not too badly. For A, our pH is 3.24. Is that acidic or basic? It is acidic. Lower number on the pH scale means more acid, more acidic. If that's confusing, it's because of the negatives. The negatives are why it's confusing. You could also use this H3O plus concentration, and oh, this is bigger than 10 to the minus 7. You could figure it out that way as well. They're related. This 1 times 10 to the minus 7, we found that the pH was 7. Is that acidic or basic? The correct answer is no, it's neutral. 7 is our lucky number. It's neutral. Questions? So this is one direction that we can go, but there's also a second direction that we can go, and that's the other one. So you can undo logarithms with an antilog. This lets us work backwards, so we can go from pH to H3O plus concentration. Normally, I would go through and show you how this works. But again, for time's sake, and because I think most people just don't care, this is what we end up with. This is our second formula. You don't have to memorize these, by the way, but you should know how they work. You need to know how they work. So we undo this bit. We undo our pH equals negative log 10 to the minus, or H3O plus, by doing 10 to the minus pH equals the concentration of H3O plus. So we raise 10 to the negative whatever our pH is, and that gives us our hydronium concentration. So let's use that. Let's say that we go to Sprouts. Big spenders today, right? We go to the water aisle. Ooh, fancy volcanic water from Hawaii. It's got a pH of 8.87. We remember what we learned in chemistry class because we're still in chemistry class, and it's on the screen. We think to ourselves, I wonder what the H3O plus concentration of this water is. Please find out. Anyone feeling adventurous and want to share what number they got? That's okay. Concentration of H3O plus equals 10 raised to the power of negative pH. So for us, 10 raised to the negative 8.87. Shoop. So we go to our calculator. You might have a 10 to the box, 10 raised to the power of box, put in the box, negative 8.87. You might have to press that button twice. If you get syntax error, that's the wrong answer. You press the wrong, you press the minus instead of the negative. And you probably got out, you maybe got out, if you did this on your calculator, 0 point, and then a bunch of zeros. How many zeros? Is it 8? Who knows? Something like this. That's not very helpful because that's one significant figure. So you can multiply it by a number, and that'll show you, like if you multiply it by 1,000, then it scoots everything over, and then you can see the numbers that are behind it. And it probably keeps going. So this would be 1.3 times 10 to the minus 9 for our H3O plus concentration. The other way that you can do it is you can take your calculator and you can put it in scientific mode. On my calculator, that's mode. The mode button is next to the second button, which is the first button on the calculator. And then you'll go down to where you see it says norm, and that's not Norm Macdonald, that's normal. And then you move over to psi, press enter, and then you press your clear button to go back, run the calculation again, and now it gives it to you in scientific notation. And it uses the little capital E, depending on the calculator you have. This might not work for yours. Questions? All right, we're going to do very similar calculations, but with one extra letter. There's also a pOH scale. The pOH scale uses the formula POH. That's why it's called the POH scale. The P still stands for negative log, and the OH here is referring to hydroxide. So this is a hydroxide scale instead of a hydronium scale. You usually don't see this, so it's rare. Wow, very cool. You're not going to see it at a zoo probably, but you get to see it here. So we're going to be using this formula now instead to find POH from hydroxide. And if we wanted to, we could construct a relationship between pH and POH. What you should end up with is that pH plus POH equals 14. That's the magic sauce. That's our relationship. The reason that this is nice is if you have pH and you want POH, if you don't have this relationship, you get to go from pH to H3O plus concentration to OH minus concentration to POH. So this is like the shortcut. This is the step for completing the circle. And that I also usually give if you need it on an exam or if it's relevant. So it should show up on your final. It's nice. Okay, let's find some POH values. We want to find the POH of a solution with a hydroxide concentration. That's this number. POH equals negative log hydroxide concentration. So POOH equals negative log 2.75 times 10 negative 8 7.561 would be our POH. How do we undo POH? Because we can also undo POH. The way that we undo POH is the same as the way that we undo pH. We take 10 to the minus POH, and this gives us back our concentration of hydroxide. So the pH and the POH stuff, it's the same formula, just one of them has an O in there. And sometimes you'll see one is H3O+. So same formula, same buttons on your calculator. We're just talking about different scales. It's the same, they're just opposite scales. Okay, so our hydroxide concentration for a solution with a POH of 3.54, 10 to the negative 3.54, calculator says 2.9 times 10 to the 4, negative 4 molar. pH and POH are one of the few places where we kind of just appear and disappear units. The same checks apply, by the way, for POH. This negative 8. 8 is close to 7.5 plus or minus 1. Probably didn't screw up. 3.54 close to 4 plus or minus 1. Probably didn't screw up. Bonus question. This solution, this top one with the POH of 7.561, is this acidic or basic? It's acidic. So the POH and pH are reversed for acidic basic. If we calculated, if we did 14 minus 7.561, this gives us our pH, and it would be 6.439, which is below 7, which means that it's acidic. And we've got a couple more slides that I want to talk about very quickly, but not too quickly. Buffers. I'm just going to mention buffers. I don't think it'll show up on the final, probably, if I'm feeling nice. I'm feeling nice. Buffers. What's special about buffers? Buffers contain significant amounts, comparable amounts of a weak acid or weak base and its conjugate. Has to be weak, has to have the conjugate. And the reason that this is special is the weak acid does not completely ionize in solution, so we have some of the weak acid parts left in solution. We also have the conjugate base that's in solution. The conjugate base is a base. It can act as a base to neutralize acid. The weak acid is an acid. It can act like an acid and neutralize base. So when you've got a buffer solution that's got weak acid or weak base and its conjugate, it will neutralize both added base as well as added acid. Our blood has a buffer in it, which is great because our blood pH needs to be in a range that's relatively narrow. It's usually 7.36 to 7.4. If it goes below 7, acidosis, I think. If it goes above 7.8, also bad, alkalosis, and you die. Because we have buffer in our blood, we can neutralize both acid and base. So looking at an acetic acid sodium acetate buffer solution, acetic acid is a weak acid. It's one of the ones that you memorize. Sodium acetate is the conjugate base. So if you add base to this system, hydroxide, it reacts with the acid. It forms some of the acetate. If you add acid, it reacts with the acetate that's in solution and forms acetic acid. So it can neutralize both, and because it can neutralize them, the pH doesn't jump up or down super rapidly when you add acid or base, which is cool. And there's some picture versions and then identifying which of these is a buffer solution, which we're not going to do today. That's all for chapter 11. Any questions?